Hey students, wanted to create a quick walkthrough video of the two chi-squared practice problems that I introduced today. So hopefully if you were maybe a little bit confused on either one of these, that this brings some clarity. So let's go ahead and read this one together. It says, in a flowering plant, white flowers are dominant over red, and short plants are dominant over tall plants. When two double heterozygote plants were crossed, the resulting phenotypes were observed, and we have our values here. So we are crossing two heterozygote parents like this, and the first thing that we're going to do is we got to find out our expected phenotypic ratio, because we're ultimately going to conduct a chi-square test to determine if these observed values are significantly different than the expected phenotypic ratio. Okay, before we get into finding that phenotypic ratio, let's go ahead and just put into our table here what we already know. So let me add these to our table. Okay, so here are our four phenotypes, and then we were given what was observed. So 206 white and short flowering plants, 83 red and short, 65 white and tall, and 30 red and tall. And that gives us a total of 384. Okay, so there are a couple ways that you can go about finding the phenotypic ratio, which is what you need in order to determine the expected values. The first, as a shortcut, whenever you see a cross like this, it's called a dihybrid cross between parents that are heterozygous for both genes, the phenotypic ratio will always be 9 to 3 to 3 to 1. And what this means is that 9 out of, if you add these all up, it's 16. 9 out of 16 is the fraction that represents the amount of offspring who will have both dominant phenotypes, meaning the white and the short phenotypes. The 1/16 will represent the proportion of offspring that will have both recessive phenotypes. And then these middle threes represent the offspring. 3/16 will have the dominant form of the trait for flower color, and the recessive form of the trait for height. And then the other 3/16 that represents having the recessive form of flower color and the dominant form of height. Okay, that's the shortcut. Whenever you see this kind of cross, the phenotypic ratio is 9, 3, 3 to 1. But I want to show you where that comes from. You can do this by making the large Punnett square, or you can do this by doing some straightforward probability calculations. So I'm going to walk you through one of those calculations to give you an example. Okay, so let's take the white short phenotype. Okay, so the first thing that you want to do is you want to find all of the possible genotypes that are going to give that phenotype. And just for reference, again, white flowers are the dominant form of the trait, and short flowers are the dominant form of the height trait. So this is representing the phenotype where we have both dominant forms. So that means as long as the offspring has at least one dominant allele for both of those traits, they're going to have those two phenotypes. So the possible genotypes will be the case where you have a homozygous dominant offspring. You have a offspring that's heterozygous to both genes. And then you have the possibility of being homozygous for one gene and heterozygous for the other, like this, and the other one would be this. So looking at all of these are all possible genotypes that can originate from this cross that will give the same genotype. And so what you can do is you can think about the probability of each one of these genotypes, and you can add up those probabilities to determine the overall probability of this phenotype, right? Since this phenotype can be any of these genotypes. Okay, so let me show you how you can do that. You can make just the single Punnett squares. We'll make them for both the gene B cross and gene E cross, right? So again, I'm just taking the genotype from parent 1, putting them on one side, and then doing the same for the other, okay? All right, now looking at these are identical Punnett squares, okay? We can determine the probability of each respective genotype. Okay, so let's start with this first option, okay? Move some of these arrows out of the way here. Okay, so the first option is the homozygous dominant for both genes, genotype. Now looking at the Punnett squares, for gene B, that's going to be 1/4 of the offspring. It's a 1/4 chance that the offspring is going to have homozygous dominant for B, and 1/4 for E. The chances of that happening in the same genotype is going to be 1/4 times 1/4. That's the chances of those events happening together, and that is equal to 1/16. For this next genotype, this is a situation where you have heterozygous genotypes for both. Looking at our Punnett squares, it's a 50% shot for gene B that the offspring is going to be heterozygous, and 50% shot that the offspring is going to be heterozygous for gene E. So we've got 1/2 times 1/2 gives us 1/4. And then for these, it's going to be a mixture of these. So we've got homozygous dominant for gene B is 1/4 based on this pedigree. And heterozygous for gene E is 1/2. We saw earlier, so this is going to be equal to 1/8. And then this is going to be the same, just in reverse. We've got 1/2 probability of getting heterozygous for B and 1/4 for being homozygous dominant for gene E, so that's 1/8. So the chances that the offspring will have any of these genotypes will be the sum of these probabilities. And if you actually add these up, this equals 9/16. If you do this for the red and short option, you're going to get 3/16. The white and tall, you're going to get 3/16. And for the red and tall, you're going to get 1/16. And so that's where you get this 9/3/3/1. Okay, so with that in mind, we can actually now calculate our expected values, right? Because we know the total number of plants that were observed was 384. And based on this proportion, we would expect that 9/16 of the plants should have this phenotype based on what we just calculated. So it'll be 9/16 times 384 gives us 216. Okay, and I'm going to do the same thing for the other phenotypes, but again, I'm going to use the correct fraction. So for the red short, it's going to be 3/16. The white tall will be 3/16, and the red tall will be 1/16. We're all multiplying by 384. Okay, so those are our calculations It's always a good idea to double check to make sure what this adds up to. This should still add up to 384. These should match. Okay, so now what we're going to do is we're going to finish the rest of the chi-squared calculation. So we have our observed phenotypic ratio. Now we need to conduct a chi-square test to determine if your observed phenotypic ratio is significantly different than the expected phenotypic ratio. So again, just like I did in class, I'm going to take my observed values and I'm going to subtract my expected values. So this will be -10, and I'll go ahead and finish the rest of these columns. I'm going to take those values, I'm going to square them to get rid of the negative. And then I'll conduct this last part where I'm going to take that 100 and divide it by my expected value for this row, which is 216. Okay, so let me go ahead and go through the rest of these and we'll find out what we get for our chi-square value. Okay, so I've gone through and I've done the rest of the calculations here. Just want to highlight real quick, it's important that, especially when you get to this last column, that you're dividing with the correct value, right? So you're taking this observed minus expected squared value and you're dividing it by the specific expected value for that row. All right, so for this first row, the expected value was 216. So I want to make sure to divide by 216. For here, the expected value was 72. So I want to make sure to divide by 72, and so on and so forth. A common mistake that I see here is students will use an observed value to divide by, and that will give you an incorrect chi-square value. So we always want to use that expected value as the denominator there. Okay, and then once you've done that, you're going to add up all of these values to get your chi-squared value, which I've done here. I've got about 4.32 was my chi-squared value. I'm now going to take this and I'm going to go to my chi-squared table to interpret my result. Okay, so here is my chi-squared table. First, I got to find my degrees of freedom. So we have 4 possible outcomes for my phenotype. So my degrees of freedom, again, is found by subtracting 1 from the number of possible outcomes. So my degrees of freedom will be 3. My p-value will always be 0.05. So therefore, my critical value is 7.815. So in comparison to my chi-squared is less than my critical value, and so therefore I am going to accept my null hypothesis, which was that differences between my observed and expected values are not significant. They're just due to random variation. Okay, so that was our first chi-square practice example. I hope that was helpful as I went through and walked through the calculations, but of course reach out if you have any questions before I talk about example number 2. All right, so for this second example, which is a little bit of a challenge, this was looking at a sex-linked trait. And from the instructions, we learned that colorblindness is a sex-linked trait in wombats. A female who is a carrier of the colorblind allele mates with a male who is colorblind. So from that, we can determine that since the female is a carrier, this gene must be on the X chromosome, and that it also, the allele for color blindness is recessive, since you can't have carriers if the allele is dominant. So let's go ahead and indicate the cross over here on the left-hand side. So a female who will have 2 X chromosomes, and she's a carrier. I'm just going to use uppercase and lowercase r to indicate her genotype. So she's a carrier for color blindness, but she does not have color blindness. Again, the lowercase r is the allele for color blindness. Okay, and she is mating with a male who is colorblind. So his genotype will be XY, and his copy of this gene will be the recessive allele. Okay, so then first we got to find out the expected phenotypic ratio so we can figure out if our values are significantly different or not. So to do that, we're only tracing one gene here, but since it's sex-linked, it's a good idea to draw the Punnett square. So I'm going to put the female on the top of our Punnett square and the male on the left-hand side, like this. Okay, I'm going to fill in my Punnett square. Okay, and we have our 4 possibilities that are going to be 1/4 probability for each one of them. So let's match these up with our phenotype. So normal female, meaning no color blindness, that's going to be this genotype right here. It's going to be 1/4 probability. The colorblind female will be right here. The normal male will be here. And the colorblind male will be there. So because each one of these will be 1/4 probability, the expected phenotypic ratio is just going to be 1 to 1 to 1 to 1. They should be equivalent in number. So let's go ahead and fill in our table here. Okay, so there are my phenotypes and the observed values, and I've added them up to get 518. So now we can calculate our expected values, which is where we're going to take our phenotypic ratio and apply it for each phenotype. So again, every phenotype should be 1/4 probability, and so you're going to take 518 and multiply it by 1/4 for all 4 of these. Okay, so I've gone and added the expected values, which should all be the same, since again this is a 1 to 1 to 1 ratio according to what we predict in our Punnett square. And that comes out to 129.5, and that should all add up to 518. So now what's left to do is just go ahead and fill out the rest of the table to calculate your chi-squared value. Let me go ahead and fill that out for you, and we'll find out what our chi-square value is. Okay, so I've gone through and filled out the rest of our table here. I end up getting a chi-square value of about 0.7. So that 0.7 value I'm now going to take and compare it to our chi-squared table. Okay, so here's our chi-square table. Again, our degrees of freedom will be 3 again, because we've got 4 possible outcomes. So we subtract 1 to give our degrees of freedom, which will equal 3. Okay, our p-value will still be 0.05, and so our critical value will be, again, 7.815, and our chi-square value is far below our critical value, so we will, again, accept our null. But the differences between our observed and our expected values are not significant. Okay, so I hope that was helpful. Again, slightly different in that we're working with, in this case, sex-linked trait, but same concept of testing our null hypothesis with a chi-square test. All right, if you have any questions, please don't hesitate to reach out, but I hope that provided some clarity about these chi-square problems.